Hello, my name is MCAT Mirabi. In this video, I'll give you a glimpse of how I teach online classes. Thanks for watching. First of all, let's study about Newton's law of viscosity. Newton's law of viscosity states that the shear stress in a fluid is directly proportional to the velocity gradient. So what is a velocity gradient first? This is a fixed plate. This is a moving plate. Consider that this plate, the upper plate, is moving at a velocity of v here. And the distance between these two plates is d. Okay, let's take this direction as x and this direction as y. So now we know that the liquid or fluid here sticks to the solid plate. So if the moving plate is moving at a speed of v, the top layer of the liquid or fluid is moving at the same speed here. And because the bottom plate is fixed, the velocity of the fluid here is 0. Now here velocity gradients will be formed, because as y changes, the velocity changes here. This velocity profile or velocity gradients can be linear, or it can be curved. For example, it can be like this. It can be like this. So this is the v or v max, and this is the y direction, starting from the stationary bottom plate. So at every point we can write that the velocity gradient times the viscosity equals shear stress. What is shear stress? Shear stress is the F over A. F is tangential force, as talked about last session. If you apply a force here to the top plate, the force over area is shear stress. The force is tangential force or shear force. So sometimes rewriting this formula, if the profile is linear, if the velocity gradient or velocity profile is linear, this term can be written as mu times v over d. Because in the linear velocity gradients, we can du over dy everywhere is the same, and it is v over d. Okay, so sometimes Newton's law of viscosity is written like this: F over A, which is the shear stress tau. This is a Greek letter called tau, and the unit of tau is of course Pascal. F over A is equal to mu v over d. So this is sometimes the Newton's law of viscosity is written like this. And this I unit of viscosity is Pascal seconds. It's clear that it must be Pascal second. Why? Here we have viscosity. Viscosity is sometimes written by shown by mu, sometimes shown by the Greek letter eta. So no wonder if you see this formula like this: tau equals eta times v over d. Eta or mu is the same viscosity. Okay. Let's work with this formula for now. Mu. What is the unit for mu? The unit for tau is Pascal. This is meter per second. This is meter. So we have 1 over second here, and this 1 over second times the dimension of mu is Pascal. Therefore, dimension of viscosity is Pascal times second. And if Pascal is written as Newton per meter squared, we can write the unit of viscosity as Newton second over meter squared. Okay. Let's talk about the factors affecting viscosity. Let's see if what happens if temperature in a liquid changes. If temperature in a liquid increases, the viscosity decreases. For example, warm honey has a lower viscosity than the warm honey has a lower viscosity than cold honey. Or consider milk. Hot milk is more easily can be moved or flown than cold milk. So hot milk has a lower viscosity than cold milk. It is the same with other liquids. How temperature in gases affect the viscosity of gases? As the temperature increases in gases, particles move faster and viscosity increases. Why viscosity increases? Because, you know, the particles of gas are moving like this. The particles of gas are moving like this in every direction. So if you increase the temperature, the average kinetic energy of the particles get greater. So if you want to cut layers of the gas, because shear stress is applying, and then we want to move like this. Tau equals mu times dv over dy. This is the velocity gradients, this is shear stress, this is viscosity. If we apply a shear stress, which is the moving force to cut the layers of the gas, you know, when particles are moving faster, the gas has a greater resistance. So when temperature of a gas increases, it has more resistance to flow. Viscosity gets greater. Another point to mention here is that this is the formula we have. Okay, tau equals mu v over d, or tau equals mu times dy over dv. If we have the same velocity gradients for water and honey, for example, we want to compare these two cases. If the same profile is there, which one means the greater force? The answer is clearly honey, because du over dv or v over d is the same for both cases. The greater the viscosity, the greater the force is needed. So to get the same velocity profile, much more force is needed in the case of honey than in water. And we can say we can apply this formula with the same force. For example, in the case of water and honey, when the same force is applied for both cases, water, when the gap between two plates are filled with honey once and once with the other time with water, if the force is the same, the velocity v over d or velocity gradient is much less in the case of honey, because mu is greater, so the velocity gradient is less, because the product of these are the same. So the greater the viscosity, the less the velocity gradient. And in the case of water, the velocity gradient will be greater because viscosity is less. Okay, so another factor affecting viscosity is nature of the fluid. The thicker fluids, for example honey, have higher viscosity. Okay, glycerin is another example. Glycerin is a colorless liquid which is viscose, but we'll see in the upcoming slides that honey is much more viscose than glycerin, and then glycerin is more viscose than water. Okay, this is an example. A flat plate of area 0.1 meters squared. This is an example about Newton's viscosity, Newton's law of viscosity. So area is 0.1 and moves horizontally at 0.2 meter per second over a stationary layer of oil which is 1 millimeter thick. So the distance of the layers is 1 millimeter or 1,000th of meter. The velocity is 0.2 meter per second. All the units are written in SI. The viscosity of the oil is given to be half. So mu is half Pascal times second. Find the viscous force between the layers. Assume linear velocity gradients. So here we're assuming that there is a linear velocity gradient here. The top plate is moving with velocity v. The bottom plate is stationary, just like the previous slides. Now we can write F over A, which is the shear stress, equals mu times velocity gradients. So F is the unknown. A, let me replace all the values we have. So half times V is 0.2 and D is 1,000th of meter. So 1,000, this must be multiplied by the numerator, and 1,000 and the denominator comes up to be 1,000. So 5 times 2 is 10. Therefore, force is 10 Newton. Okay, a force of 10 Newton is needed in this case. Okay,